What does quantum testing mean for now and more importantly for future? Welcome back to A4Q Testing Summit. We are streaming live from Marrakesh. Now we are here to answer this question. Here we have a founding member of the Moroccan Software Testing Committee, IREP trainer, and member of the ICQB exam working group and trainer, Jean-Baptiste Croigneau. Welcome to Jean-Baptiste. And Jean-Baptiste, the stage is yours.
Yes, thank you. Hello to everybody. I'm very pleased to be back on the A4Q World Congress for the following of my last presentation about quantum testing and quantum computing. So we will start with a little summary of the previous episode, and then, of course, I will add some new things about quantum testing and quantum software development and things like that. So, like you know, or if you already watched my previous video, I'm not an expert of quantum software, but I'm very interested or curious about this and what it means about testing, of course. But before to test, of course, everybody has to understand what is exactly quantum software or computers first, then software, and of course, testing. Okay, so where is my presentation? Okay, that way. So first, summary of the previous episode. What we saw the last time is, of course, quantum computing is based on quantum physics, of course. It's not an easy field, or it's quite complicated and not intuitive at all. There is a lot of specific effects or aspects to quantum physics. We saw last time, or we talked about quantization, wave and particle duality, superposition, entanglement. So I won't explain all this again. Just to remember a few points that are very important for quantum computing. The first one is, of course, the basics of quantum computing, and the basics are qubits. It means that in traditional software development, or computers, we use bits, and now, or in quantum software, we will use qubits. And the difference is very important because bits are, as you know, or a 0 or a 1. When qubits are, depends on the nature of the particle, you can use a photon or electron or anything, but these particles have some quantum metrics, and these metrics are not 0 or 1. There are a probability to be a 0 or a probability to be a 1. And it's very important because then you don't have only two values. You have, in fact, an infinite number of values. As you saw on the qubit sphere on the right, 0 is on the top of this sphere, 1 is at the bottom, but at any time, the real value is not known, is between 0 and 1, with a certain probability to be a 0 or a certain probability to be a 1. And then during calculation, this probability will evolve. And of course, it will allow us to make some very complicated calculation with only a few qubits. You can, of course, have a lot of information in one qubit. There is some other important things like entanglement, meaning that, like you saw in the previous presentation, quantum particles can be linked together, meaning that when you measure one qubit, so you know that after the measurement, the qubit will be, that at that time will be or a 0 or a 1. There is no more probability. Then the other qubit that is linked to the first one will take the same or the opposite, it depends on the characteristic, but will have also a deterministic value. It means that at the time both particles have a certain probability to be a 0 or a 1 due to superposition. But at the time we measure one, then we also know the value of the other one, even if you have a very, very important distance between the two particles. So there is no delay. It means it's at the same time, both particles take the value you measure. We won't use this a lot in our presentation, but it's very important for quantum computers. And last point, also very important, that the qubits can be stored or copied, because to store or copy a qubit, you need to measure the value. And when you measure the value, you have no more probability. So you can't copy in between value of the qubit. You can store only 0 or 1, like in traditional computers. So during the calculation, you can have any value, or any probability of a certain value. But when you want to know the value or to copy or to store the value, then you will have with certainty a 1 or a 0. Finally, for the summary part, just to remember that qubits, or maybe I can start with bits, are used with some basic gates, OR gates, AND gates, or NOR gates, or things like that. So it's a logical computation, quite simple, even if you need a lot of bits to, of course, make some great calculations. When for qubits, we use some quantum gates, and those gates can be very different, doing some simple things, like the first one on this slide. You see the X gate that will just transform 1, 0 to a 1 with a 100% certainty. So there is no probability here. We are sure that the value after this gate is no more 0, 0, 0, 0, but 1, 0, 0, 0. But you have some more complicated or more sophisticated gates, like this one, who will reset the probability. And then you have, for each qubit, an equal probability to have or a 0 or a 1. So here you have the 16 possible combination between the 4 bits, and you have an equal probability for each value. It means the qubit register, like a bit register, the qubit register can be any value with an equal probability. And then we use another gate that will transform this in a back to 100% 1001. So that's the way we can use qubits and transform qubits and do calculations with quantum computers. Okay, we can stop here on the theory to go and see what is software development for a quantum computer, so quantum software, we could say. And as you can see, it will be divided with several layers. So the first layers, if we start at the top, will be the application layer. And this is classical software. So this is not quantum software, it's classical software with a classical computer. And this application will just drive the quantum logic or the quantum computer or the quantum processor, just to tell the quantum processor what he has to do. Then we enter the quantum layers. First, generally with a generic language, so it can be or a graphical language or some code like we are used to have. And in quantum software today, they mainly use Python language or something that is like Python. And it can be divided with some specific language to a high-level quantum source code. Well, but at this level, we are completely independent of the quantum computer or the real hardware we will use later. So it can be used for any computer, any quantum computer. Then we will compile this code. So we can talk of macro assembler code. So it's this time we transform that graphical language or code language into gates, quantum gates. In the same way we can, or the compiler can make some optimization, of course. And you can already execute this code, but only on software emulators. So it's not a real computer, it's an emulator that can execute this code and, of course, maybe do some tests on this code. After that, of course, if you want to use some hardware, some real quantum computer, you have once again to transform the code into a hardware-specific source code. We will be able to use this code on a hardware-specific emulator or hardware, so a real quantum computer. We have, like we saw also in our last, or my last presentation, some very different hardware, but of course, this is why we need some specific quantum source code specific to one hardware and not to the other one. Okay, so that's it. That's how we can make some quantum software and execute this software on a quantum processor or computer. How to develop quantum software? You have also several tools. like I said before, you can use a graphical tool like this one, the IBM tool. So you can see the graphical parts here with some gates at the top that you can, of course, put on your qubits, and you can make a chain of gates, and you have already an estimation of the result of what we call an algorithm of gates, or quantum algorithm. You can also see on the same tools the code, the equivalent of this graphical algorithm in code algorithm. You can see also another tool here called Quirk. You have also a graphical part, and you have more details on what will happen to all your qubits here when we will execute this algorithm. So it's maybe a little bit more detailed on this part, but it's also so it's a free tool, open source tool, but of course, as you can see, the interface is a little bit more basics. That's the IBM one. And here you have some code, like Python code. You can do the same thing, of course, but there is no graphical view. So you create a software or an algorithm, and then you have to compile this, like we saw with the different layers. So you have your initial algorithm, high-level gate code, as you can see, with some basics gates. And the compiler will transform this in a compiled algorithm. So it's still gates, but those gates are already adapted to the hardware you will use later. And by the way, like I said before, it will do some, of course, check a little bit if your algorithm is correct. And also, doesn't mean that it's a good algorithm, but it can be executed in a quantum computer. And also, it can do some optimization if there is some duplicate gates or things like that. You can, of course, optimize the code. Then it's not finished, because after that, you have also to transform this in, well, very physical things like pulses to drive the gates, of course, and transform your qubits through the hardware. Now, we are arriving to the software testing, finally. So I already presented this slide at the end of the first presentation. It's just to mention that you can talk about very different tests on quantum computers. First, of course, to test the computer itself, because as you know, quantum computers are not very reliable today, at least. Of course, there is some progress, but we still have some issue with some kind of noise that on the hardware, that and because of that, you can't predict the result with 100% certainty. It's why very often you have to repeat the same calculation several times, hundreds or thousands times, and then make some or some statistic to know which should be the good result. That's one of the main issue today about quantum computers. So of course you have to test that and maybe to verify that this noise is not too important and that you have not too uncertainty about the result. Then you have, of course, the coprocessor controller. So this is the classical part of a quantum computer. So it's classical software, classical hardware, but we needed to control the quantum processor or coprocessor. And you have to test this also because it's quite new, of course, with those computers. The emulator, like you saw before, if you want to test your software on emulators. You have the gates. So each gates and each new gates, because you can create also some gates. It's very complicated, but of course, some experts do this, and you can find sometimes you have some new gates that are published. And of course, once again, you have to test each particular gate. And finally, you have the algorithm, meaning the real quantum software. And this is what we are talking about in the slide after this one. So we are talking about, but like in classical software, verification, validation, black box testing, white box testing. So the same terms, but maybe not always exactly the same thing behind these terms. So first, verification. Verification here is mostly about, are we building the product in the right way? So is the algorithm, your code, or maybe the documentation, are they correct? So you don't know if the result is good or not, but you did things in the right way. And for the first part, we have already some issues because it's quite difficult to detect some defects when you watch a big quantum algorithm with a lot of gates, very complicated gates, with some linked effect between qubits or between gates. So to find a defect may be very difficult if you just watch maybe the graphical algorithm. So it's not easy. Maybe sometimes you can look a specific part of the algorithm. You can still find some big mistakes or big defects, but it's not so easy, not as classical software. You also have validation. So this time, is, are we building the right product? So is the product working well or doing what we want to do? But there again, we have some difficulties because, well, on the black box testing part, so you just start your algorithm and see what is the result. Then, of course, you will have an oracle issue because quantum computers are so complicated using probabilistic effects that it's very difficult, of course, for a human to calculate the good result. And even for an emulator, if you use a classical computer to do the same thing and try to find the good result, well, it may take hours, days, or even years to have a result. So very often it's not a possible way to make tests. So how to know that we have a good result after a very complicated calculation? On the white box testing, so this time we can maybe execute not the whole algorithm, but only a part of it to detect some defect, maybe just after the first gate or the first two gates, and maybe being step by step to be able to verify the good result, but not only at the end of the calculation, of course. Then you can detect a lot of defects, like a problem on hardware, the quantum noise coming from, well, the environment. Because we can't isolate totally the quantum computer. So everything outside the computer can interfere with your qubits inside the computer. Of course, you can have some issue with compiler or code optimization. Very often we will try to use some error correction code inside the software, but there again, you may have some defects. And also, a very important part is the data preparation. So you can fix the value at the beginning of your algorithm. So we know how to do that, but when here also you can have some issue or defects and have some bad data at the beginning of the calculation. So that's what I already explained, but white box testing, so we can talk about debugging. The issue is you can't start an algorithm, stop, have a look to the values, and then restart your algorithm to go to further with a second or another step. Because when you stop and when you check the value, you do a measurement, and as we know, with a qubit, you have no more probability. You fixed every value. And that's not the way it works during calculation. During calculation, we need to have this probability aspect of qubits. So after your breakpoint, we could say, then you can't continue. So the only way to continue is to restart from the beginning and define in which step you want to stop, and maybe have a look to the values. But then again, you have to restart from the beginning, and so on. So it's not like classical software. And of course, it's not so easy to debug step by step. Very important to validate the software. Of course, you can use an emulator. Emulators are like perfect quantum computers. So you have no noise because it's just computers, classical computers. So you don't have this noise issue, and the result is always the good one. The good one meaning depending on your software, of course. And so you don't have to execute several times the same algorithm and do some statistics to know which is the result of your algorithm. You execute one time and you have a result, the good result. And then you can also make some interactive debugging because it's an emulator, so you can stop it at any time, have a look to the values, and then continue. But of course, emulators can't do the same thing that quantum computer, or yes, they do, but with much more time. So when you have a few seconds on quantum computers, you may have hours, days, or years of calculation on the classical computers. So you can't use emulator on every software, quantum software, of course. You can only use it on very small software or just on the part of the software. But of course, it's a good tool to debug or to test some parts of the software. So software testing about quantum computers is, of course, very new. People are still searching for solutions or how to test. And of course, we try to reuse some known testing method or testing tools. For instance, we can use mutation testing. So here you have a quantum code, a very simple software that do just an addition between the value of A and B. So very basic, but like you can see, it's not so easy to make an addition with quantum computer because it's not, we don't use quantum computers to do some very simple calculation. It's more to calculate the weather or things like that. So a lot of statement in this code. And as you can see, it's very similar. You have some kind of repetition a lot in the statements. And of course, it's very easy to maybe copy past some part of the code and do some mistakes, changing the numbers. So you have very easily some defects in this code. So you can use mutation testing, changing automatically some part of this code, and you then execute the new code and check the result. If the result, of course, is okay, then maybe you have an issue with the software because any change should change the result. If not, then you are able to detect the defect and, of course, fix the defect. So that's a way maybe to test. But once again, this is a very simple example. You can imagine that in a big quantum software, that will be not so easy. Another techniques that we could use is model-based testing that we know well in ISTQB. And like you see, you can also represent, it's the same algorithm, once again, to make an addition between two numbers. But this time we have a graphical view of the software. And of course, you can imagine that a tool will use this to define which test should be useful to maybe detect some defects in your code or in your software. And once again, this is not already possible, or maybe some experiments on some tools in some laboratories. But this is also a way to maybe find some new way to test quantum software. So this was some, let's say, software testing, quantum software testing, to test really the software itself. But like I said before, you can also test some other things like computer itself, hardware, or anything else. And so there is something that is very important in quantum computing is, of course, benchmarking, because you have a lot of companies or organizations that are developing some new quantum computers. And of course, they need to know how they work, or what is their performance compared to other quantum computers. So benchmarking will be used to compare between two computers, or to compare quantum computers with a classical computer. Very important, because we would like that the quantum computers have some, of course, better performance than the classical computers, and it's not always the case today. You can also compare some characteristic between also some different solutions or computers, like, of course, computing time, energy spent, very important today, to, yes, of course, to lower the energy needed to make some calculation. And of course, today, quantum computers need a lot of energy, so it's a characteristic that they need to improve. The cost, of course, cost is very high today, as you can imagine. And finally, of course, compare some algorithm that solves the same problem or make the same calculation, but in a different way, and see if one is more quick or more accurate or anything that the other one. So is it also part of the software testing or quantum computer testing part? And a lot of companies work on these different benchmarks. It may be linked to what we call the quantum supremacy or quantum advantage. That is the main goal to all the companies that work on quantum computers. Quantum supremacy means you have a definition here, a problem, useful or not, and that's a point, because very often today, when a company say that we reach the quantum supremacy, very often is on not useful software. So, okay, they did some very complicated calculation in a very short time, but it's we can't use it for anything, so it's not very interesting, of course. So this problem, useful or not, is only solvable with a quantum algorithm running on a quantum computer. And very important, there is no non-classical algorithm for the most powerful supercomputers. So of course we will compare quantum computers with a very, very big supercomputer. And this computer, classical computer, is not able to do the same thing in a reasonable human scale time, so in a few hours or days or something like that. Advantage, the definition is a little bit different, but it's more or less the same thing. This is a situation where a quantum computer execute but a useful algorithm, so it's the main difference, should be a useful algorithm, faster than on the most powerful supercomputer. So because you need a useful algorithm. Of course, you can consider that it's more complicated to have quantum advantage on classical computers compared to quantum, what we call quantum supremacy. There is a last point, less important maybe today, but still important. Advantage could be also that a quantum computer consumes less energy than the classical computers for solving the same problem, of course. Because if you compare 1 second on the quantum computers and 1 second on the classical computers, the quantum computers will consume much more. But because it can do in a few seconds what the classical computers will do in hours or days or weeks, then of course it will become more efficient on energy. So I'm more or less at the end of my presentation. Just to sum up what we saw, or what I tried to tell you, so a few key points. So quantum computing, is based on running code multiple times. So it's what we said before. To have one result, you need to run your software multiple times, meaning maybe thousands times. And that's a very important point, because that's why it's difficult today to have or to obtain quantum supremacy or quantum advantage compared to classical computers. So if you make only one execution, you will have a probabilistic outcome. So you have a result, but you are not sure that this is the good result. So you have to run it a lot of times and then make statistics to find what should be the good result. Second point, emulators also or today are very useful, because as we saw, it's very difficult to test or to debug on quantum computers. When on emulators, of course, you can do a lot of things. You can watch each step or each gate and each qubit, what is going on. But once again, you can't do it on a very big algorithm because it's so long to execute. Finally, yes, there is some issues today or some challenges to debug and to test quantum software. The problem with Oracle, so difficult to know what is a good result, difficult to debug, so we can't put a breakpoint and easily watch the values and then restart our software. So yes, but a lot of challenge means a lot of things to create, to a new way to test, some new tools. So maybe not for the months or years coming, but or maybe in a few years it should become a new field in software testing. So we have to look at this, and like often, maybe also it will develop some new tools that maybe we will be able to use also for classical software or classical computers. To finish, of course, some references. My presentation is based, mainly on Understanding Quantum Technologies by Olivier Ezrati, a very big book with a lot of information. You have some very detailed parts. Maybe you need some good knowledge in mathematics and physics, but also some more easy parts. And yes, very interesting. I use also an article by Macario Polo Uzalo. I hope that is a good pronunciation. So it's a short article about quantum software testing. You won't be able to find a lot of articles on this matter, of course, but it's starting, so people are searching solutions. So it's a good way. I put also Qiskit. You can use this to make very easily your first quantum software with some free tools. You can execute it on emulators or even on real computers, quantum computers that are, of course, online, proposed by Google's or Amazon or big companies. So it's very easy. In maybe let's say a few hours, you will be able to have a first software running with some first results. Thank you. That's it for me. I have no idea about the timing, if I'm short or not too long. I don't know if there is any question.
Thank you very much, Jean-Baptiste. It was interesting. Should we wait? We wait for part 3 in next summit?
Maybe.
Good. It's always a pleasure. Okay, we should jump to the next session. So please, this presentation is available on our social media channels. And if you are a member of the Skills Club, you can have access to the slides. Thank you, Jean-Baptiste. I'm sorry I had to end this session, this amazing, but I'm pretty sure that you can find the question on the social media, and I will try to send the question to you and answer the question there on behalf
Thanks
of you.
a lot.
Thanks for your
Thank
time.
you. Goodbye.
Bye. Stay with us for next sessions. Thank you.